Okay, up next, we've got a talk about fairness by Noah from Cornell. Please, Noah, take it away.
Thank you. This work is also with Alex Levinson and Justin Su, also at Cornell. Great. So let's say we have a delicious slice of chocolate cake and two hungry children, Alice and Bob. We'd like to be able to split this piece of cake up in a nice way between them. Well, what's a good way to do this? Well, we could have Bob take the cake and cut it into two pieces that he prefers equally, and then have Alice take her pick. Suppose in this case, though, that Bob really likes strawberries. However, Alice really cares more about the size of her piece. Then Bob, cutting the cake into two equally preferred pieces, might cut closer to the right, like shown here. And then, of course, Alice is going to take the piece closest to her so that Bob gets the strawberry piece. In this way, if we allocate it in this way, then both children will receive a piece such that they don't envy what the other received. So this is actually an instance of an economic problem called fair division, and specifically cake cutting. Stated, given a set of agents, we'd like to fairly divide an infinitely divisible good between them. Now, this is pretty simple to do most of the time if all the agents have the same preferences. However, we relax that assumption and allow them to have different preferences, which make this problem much more interesting and challenging. Some terminology here. We often refer to the whole good as the cake, and what agents receive of the cake after we divide it is called the allocation. And the actual process of producing the allocation from the cake is what we call the protocol. It's algorithmic in style, though it may ask agents to do things like split up one piece into two or compare some. Specifically, the protocol I described with Alice and Bob is called cut choose, and I'll refer to that in the talk in the future. But of course, what do I mean by fairly? There's a lot of notions of fairness, actually, but perhaps the most natural one for this problem is that of envy-freeness. An allocation is envy-free if no agent prefers another's allocation to their own. Stated differently, no agents would have envy over the other person's piece. And we can apply this definition on a protocol level. A protocol is envy-free if it always produces an envy-free allocation. To see some examples to get it flowing in your head, cut choose, the protocol between Alice and Bob, is envy-free. However, if we modify it so that Bob cuts the cake and picks, that might not be envy-free. Now, why is that? Well, if Bob cuts it the same way, he prefers both the left and right piece equally. Well, in that case, he might pick the piece that Alice wants, the piece on the left. Then Alice would be left with the strawberry piece. So you might be able to tell that this won't be envy-free all the time. Now, let me give you a brief history of this problem, or the protocols within it. So the first protocol is the one we described for two agents. It's ancient. Probably a lot of parents know this if they have two kids around the same age and they want cake. In this instance, the cake is cut at most once. The first three-agent protocol was introduced in 1960, and it may require the cake to be cut 5 times. Now, it took a while, but eventually a 4-agent protocol that is bounded in the number of cuts was produced. However, the number of cuts might be needed is 203. Now, the same researchers a year later generalized this to an arbitrary number of agents. You guys ready for the bound? N to the n to the n to the n to the n. Quite a bit. You might already be able to tell this problem's pretty hard. Now, let's take a look at the 4-agent one despite this. Actually, maybe not. But if you squint, you can see most of the description of this protocol is just English. So this isn't even precise. So it's even more concise than if it would be if it were formal. And this problem is not specific to just that protocol. In general, they're quite complicated to describe and require these ambiguous English descriptions. Why is that? Well, they just have a sheer enormous amount of cases that they have to consider. And of course, along with this, with the number of cases, what if one's missing, either from the description or for some correctness proof? How could we know? Well, that's where we come in. We provide language for describing cake cutting protocols. We call it slice. In Slice, we can unambiguously describe these protocols and then can translate these expressions to logical formulas, which we call constraints, in a sound and complete way. And these constraints enable us to automatically verify things like envy-freeness by taking advantage of SMT solvers. All right, before we continue, I'm going to have to give you some more background on the model itself. So the model, the cake in the model, the cake is modeled by a unit interval. A piece is an interval contained within the cake. And an allocation is then an assignment of pieces to agents. Let's take a look at an example. Here, the agent set is 1 and 2. And then in this case, the allocation is a pair. The first component goes to agent 1. The second goes to agent 2. Here, agent 1 gets the piece from a 0 to a quarter. And agent 2 gets the piece from a quarter to a half, as well as the piece from 3/4 to 1. Note that the whole cake isn't allocated here, and the piece, or the thing that agent 2 receives, isn't even connected. We allow these kinds of solutions. All right, now we have to actually model how the agents interact within the protocol. To do that, we first need to talk about how we model their preferences. These are modeled by valuations. Valuations are functions that assign a piece, each piece a value between 0 and 1, where more is better. In this case, the value of the whole cake is 1. We also assume that the value of 2 pieces is the sum of their values, provided that they're disjoint. There's a few other assumptions, but I don't think I have time to share them here. And we actually have the agents interact with the protocol by giving indirect access to their valuations using the following 2 operations. The first of which, eval A of a piece gives agent A's value of that piece. In mark, this one's a little more complicated, mark of A of a left endpoint L and a value V returns any right endpoint such that the agent A's value formed by the piece from L to R is V. So if you look at that picture that I've got there on the bottom, you plug in L and V and you get R. Now this last one's a little more interesting because there might be more than one such R for which this holds. So it's non-deterministic, and we like to be able to handle that as well. Great. Now we can finally talk about our language. Here's an example. We've put cut-choose, the protocol with Alice and Bob, into the language. And I'll go through the couple steps that it has. So of course, the first step is to divide the cake into 2 equally preferred pieces, according to Bob. Here, agent 1. Now it's highlighted in orange. Divide takes a piece and then a point and splits that piece at that point into 2. And the point that Bob chooses to split it at is this mark 1 of 0, 1/2. That point is such that the piece from 0 to that point has value 1/2 of the total cake. That way, Bob splits the cake into 2 equally preferred pieces. Following this, we just need to get the preferences of agent 2. Here, pi is just a normal projection, like you might expect, and then allocate accordingly to those preferences. So briefly, here's the syntax. I'll give you a moment to stare at it, but there's 2 pieces to this. The top part is just a standard first-order language, and the second part is the cake-cutting specific expressions. Get a drink of water. So you've probably seen by now everything here. The only thing that you haven't seen is the left E and right E, which give the left and right endpoints of an interval respectively. Finally, we can actually talk about the constraints. Those are what we take the expressions and translate into, those are the formulas that we translate them into. Intuitively, a constraint captures the possible outputs of a protocol. To give a definition, E is a closed expression, suppose that. Then the constraint is this conjunction of equating V to a term out of V, as well as rem of E. Now, out of E is a logical term that represents what E's output is, which is why we equate maybe a value to it. And then rem of E consists of the remaining conditions that out of E does not capture. Now, rem of E and out of E are defined compositionally, but I don't really have the time to give you guys the definitions here, but it's based on the structure of the expression. And with this, we have the following soundness and completeness result. Given a closed expression, E will evaluate to a value V if and only if the constraint of v at that value is valid. Well, great. How do we use that? Suppose we have a formula, is envy-free, which says that the allocation v is envy-free. But in principle, this could really be any formula that we care about. Then consider the other formula, check, which just says, for all values, the constraint of v at that value implies that this is envy-free. So that's actually a concrete expression. And then we have from soundness and completeness that the following if and only if. E will evaluate to v implies that that value is envy-free if and only if check is valid. Now, of course, we can just take check, it's concrete. We want the thing on the left, we can just give that to an SMT solver in order to show that our protocol is envy-free. Great, and this is exactly what we've done in our implementation. So we provided a prototype implementation, primarily for proof of concept, that enables us to write and run cake cutting protocols and automatically translate those protocols into their constraints, and then immediately take those constraints, pair them with a property that we care about, and give it to Z3, an SMT solver, in order to actually verify that the protocol achieves that property. And so we've done that specifically for these protocols listed here for envy-freeness. And for all of them, besides the last one, the solving time is less than 1 second. It's really quick. But the last one, Selfridge Conway Full, takes about 20 seconds or so on my own machine. That's because it's a lot more complicated than the rest of them. Great. What's next for this work? Well, right now what we're working on is being more careful about our translation and translating the expressions into real linear arithmetic constraints. This will allow us to check things faster, allowing us to scale to more complicated protocols, as well as guaranteeing that we'll receive a result from the SMT solver. It would be also interesting to verify other cake cutting properties, such as making sure that each piece is only given to one agent, or that the whole cake is allocated for those properties that actually claim to have that property. It'd also be very interesting to verify protocols for an arbitrary number of agents. But more generally, there's a lot of economic mechanisms out there. What else can we verify? So, of course, I had to leave out a lot of details here. In our paper, we have formal model description, language semantics, full constraint definition, as well as soundness and completeness proofs, some more details as ways and another way to access our actual implementation and take advantage of it and use it, as well as detailed examples of the protocols that we were able to successfully check were envy-free. So you can take a look at it. Here's a QR code for our paper. Thank you.
Hello, Ed Geringer, NC State. One of the issues that you didn't mention is whether it matters that an allocation be contiguous. In cake, maybe it doesn't unless you cut up all the frosting with too many cuts. But if you're dividing up land for like a farms, it might make a big difference. What influence does the need for contiguity have on your algorithm?
So our language verifies generally algorithms, more than just one specific one. We do also consider verifying protocols, or our system will work to verify protocols that give you contiguous pieces. But in general, that problem is much harder than generally just cutting up a piece and giving maybe this guy a piece from the left and a piece from the right.
Aditya Thakur, UC Davis. So though in theory the cut and choose is envy-free, in practice if you're actually cutting a cake, the person cutting the cake usually gets the raw deal because the divide is not exact, right? So is that something that people have looked at in theory, or is that something that you think you could reason about? For example, you flip a coin and different people have to choose, have to cut each time or something of that sort?
Well, that's a really interesting question. This model specifically doesn't capture that. I would expect the use case for a model like this to be for things that are more precise than actually cutting a cake.
But I mean, there are other physical quantities that you can't divide exactly in half.
Well, that would be an interesting
some
variant
error.
to the problem to consider for sure. But I personally haven't considered it.
Excellent. Okay, thank you.
Hi, this is Django Lee from class. I was wondering how restrictive the limitation of restricting to intervals. Does your algorithm generalize to, say, like a two-dimensional square, or in general any polyhedra?
So no, actually, the problem is like really hard if you go from. So right now we're just one-dimensional. If we were to go a second direction, then like part of the way the operations work, like the eval and the mark, like those are much easier to do because you implicitly have like a natural direction to go. But when you just increase your space, it's a lot harder to do. I mean, already the problem's really hard, like you saw the examples of the protocols. There is work, economists do study these things, but it's a lot harder to get guarantees on any things that we might like to have.
All right, thank you.
So there are some typing bubbles here in the Discord. So to give our TV land friend time to type things out, one thing I was curious about, you showed that big natural language protocol from our theory friends, and you mentioned that doing it fully formally would be even longer. So have you done a comparison?
So right now, that's currently in process. So we're.
Can you give us a sneak peek? Some intuition? Is it order of magnitude? Is it factor two?
So right now, we're only working on. So in that paper, they give a 3-agent version as a warm-up for the 4-agent version. The 3-agent version is giving us a hard time already right now. It's probably like 60, 70, 80 lines to describe the 3-agent version. It's going to take us a long time to fully write down the 4-agent protocol.
Interesting. So it seems like there's some opportunity maybe if you want, economists and folks to use a tool, there's another layer maybe even to be built to.
Yeah, there's definitely like things that we could add to make it nicer to use so that we can get economists to start writing these things down instead of just writing it in words. That would be nice.
Okay, Bruce Z, hit enter or forever hold your peace. Looks like we will handle this offline. Let's all thank Noah again.